So we have learned about the basics of what happens to an electron when it is put in a magnetic field. Okay, so so what we have learned so far is that एक minute. So this is where is it? Okay, sorry, not this one. So yes, so this was the idea that we have got so far. So energy of the state is given by, depends on ms. When field is applied, b naught is the magnetic field, mu v is the Bohr magneton for electron, ms the z component, the quantum number that tells you about the z component of the spin angular momentum, ms. So it could be it can be plus half or minus half, and so plus half is represented as alpha state, minus half is represented as beta state. So alpha minus beta, that gives you the energy difference between the two. So this is how pictorially you can represent it for an electron. And so ms minus half, that is beta state, is lower in energy when the field is applied, and alpha state is higher in energy when the field is applied. Plus half is this. So this is the direction of z component, ms h cross, z component of the spin angular momentum. Remember, unless and until you apply the field, there is no difference. Plus half and minus half will be of same energy if no magnetic field is applied. Okay, so this is also an important point, and people do make mistakes in the competitive exam. Something like this comes. Okay, so you have to, so when there is no magnetic field, there is recording is on, yeah. So there is no difference between ms plus half or ms minus half. When you apply magnetic field, only then this difference comes. And now you know why it is like this. जब प्लस हाफ होगा, the magnetic moment will be pointing. So if you think of an magnetic field that is applied in this direction, field applies is in this direction, and if the plus half spin that you are talking about, if the direction, this is the direction of the spin, then the magnetic moment mu will be pointing in this manner. Magnetic moment will be pointing in this manner. And for the other one, when s is this is like this, the spin angular momentum is pointing downwards. The z component of that, the magnetic moment mu will be pointing in upward direction. So something that is aligned with the field, aligned with the magnetic field. I told you the basic concept. When you look at bar magnet, when the bar magnet has alignment of its magnetic moment along the magnetic field direction, that is the lower energy, that gives you the lowest energy state. Remember, this is always the thing, whether it's electric field or magnetic field. Whenever you have a dipole, the moment of that dipole, whether it's magnetic dipole, whether it's electrical dipole, the lowest energy is obtained when it is, that moment, dipole moment, is aligned with the field. So here the lowest one, you see, when it is in spin is minus half, represented by minus half, it is in lower energy state. So rest of the things, so this is how you calculate. So difference is known. So greater is the b naught, greater will be the separation. And so these are the things that will happen. So beta state is the lower energy state, because, and this is we are happening, so this can be correlated to the magnetic Gyric ratio, which is negative for electron. For proton it will be opposite, because in proton the angular momentum and the magnetic moment both will be pointing in the same direction. Okay, so because of that the situation will be reversed. So h mu, so what is the resonance condition? Ge, the G factor, the mu b, the Bohr magneton, and b naught. So this is how you represent it. And this is the EPR that we can think of, typically carried out at 0.3 Tesla. So resonance will come up, there will be transitions, and depending on the nature of electron, immediate environment in different molecules, in one molecule at different places, you can have transitions are possible, and at different frequencies, slightly different frequencies, so you can get a lot of information about that if there is any unpaired electron present. So EPR is a microwave technique. I also told you about if you can just similar thing you can visualize with alpha state for nucleus, beta state. So in this case, what will happen, as I told you, so in case of this, it is a positively charged uh, proton with a positive charge spinning, undergoing a spin. So you have a, you can imagine when the spin is pointing in this way, the magnetic moment will also be pointing in this way for the proton mu. Okay, for this, when s, the small s, if I am representing, is the angular momentum, spin angular momentum is pointing upward, the dipole moment is also pointing upward. So this is the idea that you have to pick up. Aligned with the field, lower in energy. ठीक है, magnetic moment aligned with the field, if this is the direction of field b naught, and so I can see that this is getting aligned, this will be in lower energy state, and the one which is opposed to the direction of field, that will be higher energy. Simple. So this is the quantum number I, mi, that you see. I is the quantum number total summation that will give you the magnitude of angular momentum. This is giving you the direction of angular momentum along, sorry, the magnitude, direction of angular momentum, or you can say the z component. So the resonant conditions is this: h mu should be equal to gamma, this is the gyromagnetic ratio, uh, h cross into b naught. So once this condition is fulfilled, so this is also the Larmor frequency. So this you can say that is the Larmor frequency of the nucleus, and the frequency of electromagnetic radiation, this is mu Larmor, and this is the mu should be equal to this. This is the condition that we are trying to have. The Larmor frequency, that is the precessional frequency. Precessional is the spin angular momentum vector is moving along a cone around the applied magnetic field. So if z-axis is the direction of applied magnetic field, it is a precessing moving around that. So okay, so that is the idea that we are trying to take up here. So not, so this is, you have to imagine like this, that these electrons and protons, they behave as tiny magnets, and a magnet is necessarily a dipole. It has north and south pole, it is a dipole. There is no magnetic monopole. कोई भी छोटा से छोटा पार्टिकल भी आप उठाएंगे, that is exist as a magnetic dipole. It is not there is no magnetic monopole, it do not exist. So there are theoretical explanations for that, why it will not exist, but we are not going to that for this point. For our purpose, it is sufficient to just learn these points. इवन यहाँ तक ये सब चीज़ें फिजिक्स के स्टूडेंट्स को भी नहीं पता रहता है, जब पूछते हैं तो कोई नहीं बता पाता है. मैग्नेटिक मोनोपोल डू नॉट एग्जिस्ट. इलेक्ट्रॉन इज अ इलेक्ट्रिकल मोनोपोल बट अ मैग्नेटिक डाइपोल. समझ रहे हो? So if you had isolated electron, it has spin, it is electrical monopole, but as a magnet, it will, in a magnetic field, it will behave as magnetic dipole. So this you are seeing the motion. So plus half means this. You have apply the right hand thumb rule. You can see your thumb will go up. So this is the up spin, plus half, and this is the down. The thumb will be pointing in this direction. So this is how we differentiate between the spin energy states. So north south, south north, like this, and this is a, okay. So if it is a positively charged, then it is aligned with the field. The mu is pointing in this direction, and for this the mu is pointing in downward direction. This is, so if it is a proton, if this is a proton, this is also then proton having two different spins. If you can think of this way, So this is what we are talking about. When it is aligned with the field, it is having lower energy. So this one is lower energy, and when it is opposed to the field, the mu is pointing opposed to the field, this will be of higher energy. Okay, so this is the transition. Obviously, when the energy is absorbed, it changes from one to the other, from the lower energy to the higher one. Okay, so that is what we mean when we say that electromagnetic radiation is being absorbed, and the spin changes. So what changes which occur, this is the change that will happen. Something that was aligned, now it will become opposed to the field when you give some energy. So the nucleus that we have been talking about is like so simple consideration of a spin half nucleus. If you take, this is the situation. So 13C, 19F, 13P, 31P. So these are very important ones. In chemistry, you will find that these are, for NMR can be done on this. If a molecule contains these atoms, you can uh, perform the NMR spectroscopy on that, because it will respond to the magnetic field when you put it in the magnetic field. So this is a typical thing that you have in a your NMR spectrometer. In a NMR spectrometer, this is the thing that you have. Uh, so what do you see? There is a superconducting magnet. So superconducting something, for something to be a superconductor, usually you have to bring it to a very very low temperature, or around 4 Kelvin or something. So to reach that temperature, what do you use? Use liquid helium. So these are the complications in running NMR spectrometer. You need to have a liquid helium to cool this, achieve superconductivity, and then the magnetism, you will get the desired uh, magnetic field of highly intense uniform. So you need to, so you need a source of uniform intense magnetic field. So you need a magnet, and you also need a source of electromagnetic radiation. What type of electromagnetic radiation? The radio waves. When we're talking about nucleus, the range comes about in the range of जो FM रेडियो आप सुनते हैं, लगभग उसी, समझिए कि उसी रेंज में काम करेगा, उसी वो वाली रेडिएशन एब्जॉर्ब कर सकता है न्यूक्लियस, और उसका स्पिन फ्लिप कर जाएगा. Spin, there will be spin flipping of spins for alpha to beta state. So spin flip occurs when the energy in this range is absorbed. So usually you have a, you need a force. So 10 Tesla minimum, usually you require a magnetic field of 10 Tesla, something around this. So you need a magnet, usually a superconducting magnet, which is capable of doing this. Remember, in EPR we are able to achieve that same almost the थिंग विद द 0.3 टेस्ला. हमारे काम का सिग्नल आ जाता है जब 0.3 टेस्ला. तो यहाँ पे हमें ज़्यादा एफर्ट करना पड़ रहा है, क्योंकि सिग्नल बहुत वीक होगा. अगर इससे कम स्ट्रेंथ का आप मैग्नेटिक फील्ड यूज़ करते हैं, then it will be much weaker signal that you will obtain in the detector, and nothing significant you can analysis you can perform. So you have a magnet, और उस सिलेंडर की तरह होता है. It is a cylindrical magnet. You put your sample in that. So the magnet is at 0, some temperature approaching around 0, not exactly 0, 4 Kelvin around. And but the inside this hollow space that you have, that is may be kept at a room temperature. So sample may be at a room temperature, but the magnet has to be at very very low temperature. So liquid helium is required around that. So sometimes to remove inhomogeneities, rotation is done, but that is not desirable. Do not rotate it. because sometimes that also gives different kind of results which are not reproducible enough. सो साइंस में सबसे ज़्यादा जब भी आप रिसर्च करते हैं, एक्सपेरिमेंट करते हैं, द आइडिया इज़ टू गेट रिप्रोड्यूसिबल रिजल्ट्स, देन ओनली इट इज़ एक्सेप्टेबल. So if for some reason you are getting irreproducible, then it has no meaning. So sample spinning is avoided, जहाँ तक हो सके अवॉइड करते हैं. And liquid helium is used at 4 Kelvin. Sample, but the sample is kept at room temperature in most of the cases. So intensity of signals will depend on two factors. One is the difference between alpha. So this is the difference between the spin states, difference in the population of two spin states. So alpha and beta का जो आप देख रहे हैं कितना population होगा. So if you have say 100 of nuclei are present, how many of them are in alpha state, how many of them are beta state at a given temperature, at room temperature say, if you're trying to. So that difference is essential because उसी के basis पे तो transition होगा. जो lower energy state में होगा जितने population होगा तभी तो ऊपर वो जाएगा. अगर वो कम हो गया somehow. So for example, in a nucleus you have to go from alpha to beta. So of course that how many of them are the relative population matters. And the second thing that you are seeing, that is the applied magnetic field. So this is another factor that will affect the intensity. Further, if you try to find out how does it depend, ये कैसे n अल्फा n बीटा जो है माइनस n बीटा ये किस चीज़ पे डिपेंड करेगा, अल्फा एंड बीटा स्पिन स्टेट्स में कि पॉपुलेशन का डिपेंडेंस. Then you will find that it is the gamma here is what? It is the gyromagnetic ratio, H cross, again a constant, and by 2 kt. So n is the total number of both alpha and beta states. So total number of population. So n, that is you are talking about n alpha plus n beta. N beta is equal to n. So this is what is represented here. So then that is n, and so keeping it like this. So you are getting a B naught term over here. So you can see here, if this is having a B naught term, intensity now will have so intensity. So the population difference is having a B naught by 2 kt. This is the term. So overall, if you realize carefully, it is a B square. Magnetism is a square of the magnetic field. The dependence is, so magnetic, the effect of intensity is very, very sensitive to the applied magnetic field. Okay, because you are getting a B square term now. The first term, the population difference, also depends on this B naught. So obviously it is taking it together, we are having a B naught square term coming in overall thing. So intensity is likely to be more sensitive, much more sensitive to the magnetic field, because the population difference also depends on B naught. So this is what proportional to B naught square. And NMR signal is will be enhanced to a good extent if you increase the strength of the field. Magnetic field जितना बढ़ाओगे उतना अच्छा सिग्नल आएगा NMR में. So it can so ये रिलेशन हमें यहाँ से पता चलता है इंटेंसिटी. So ये रिलेशन हम यहाँ से देख रहे हैं. Clearly you are having a B naught square term coming in, which really helps. So it makes sense. And दूसरा factor, the second factor is that Magnetogyric ratios. If you compare the Magnetogyric ratio, like of a proton, H1 and hydrogen atom H1 is magnetogyric ratio for hydrogen is much more as compared to magnetogyric ratio of 13C. 13C. If you want to see, go back. Let's go back to the previous slide. We have the data to highlight this point, which will be easier to understand. एक मिनट ये पीछे जाना पड़ेगा एक कहाँ गया कहाँ गया कहाँ गया oops where is that हाँ ये वाला sorry so just what we are saying that another factor that will affect your signal so this a third factor that we are saying now uh, rather is that magnetogyric ratio so look at the hydrogen this has a magnetogyric ratio of 26.75 look at 13C 13C has a magnetogyric ratio 6.73 so you can expect your signal to be much more for the same applied field same strength of the applied magnetic field the signal obtained the NMR signal that you will obtain will be much greater in proton magnetic resonance so PMR H1 NMR will be much stronger going to be give you much stronger signal for the same strength of applied magnetic field the intensity of signal will be much better so that this is the point that I was trying to tell you and that's why we had to go to the previous slides so to elaborate this so you have something around 6 magnetogyric ratio was around 6 sorry 26 here and 6 for this so you can see that they are much more intense than yes than the small and the value for 13C the signal will be less intense for the same kind of thing okay so now we also talk about yeah there's an important term that will you will in fact all the data is plotted in terms of chemical shift nowadays not in terms of the frequencies so so nuclear magnetic moment so your magnetic moment of the nucleus or moment of the dipole magnetic dipole which magnetic dipole the nucleus is being treated as a magnetic dipole so we have a magnetic dipole the nucleus itself and that magnetic dipole will interact with the local magnetic field किसका आ गया एक मॉलिक्यूल में उसके अराउंड इलेक्ट्रॉन्स होगा उसका भी कुछ अपना फील्ड होगा so local magnetic field so this is the local electrons and other elements in so you environment is there so primarily it is electron you can immediately around the nucleus you have electrons around it so they will also have their own magnetic field a dipole produces is a magnetic dipole will have magnetic field associated with it an electrical dipole will have electric field associated with it okay so think in those terms local field so so it is different from the applied field so so we have a local field may arise because of mm, electron you have angular momentum due to orbital motion of electron you have spin of the electron so both of them might contribute so you can that can give rise to additional magnetic field at the nucleus so this local field is important to understand and for the same nucleus say proton hydrogen 1 nucleus under different conditions so if the bonding situation changes you will have different local field produced and that will shift the Larmor frequency will be different for the two different environments. So we primarily we can try to understand this additional field that is being created. So you are applying a field B naught, and you find a local field that is created because of electrons are setting around it, the nucleus are getting uh, also interacting with that, and you have a change in field that is given by delta del B, and this is minus sigma B naught. It can be equated to the external field that has been applied. This is the external field, externally applied field. So, and sigma is the shielding. So this is the shielding constant for the electrons around it, electrons around the nucleus. And yes, so when we write it, so we can, the total net field will be written in the, so it is called the shielding constant, dimensionless quantity, and usually positive but maybe negative. So depending on positive shielding constant, matlab you have a good, the nucleus is getting shielded by the electrons present around it, and you are not, so this layer of outer electrons do not allow the external magnetic field reach the nucleus with the same way. So some weakening because of the shielding you can expect. And if it is somehow sometimes we will see where it can be, where it can be positive or negative, that we will see later with examples. But mostly you will find that this sign of the shielding constant is usually positive, and when it is negative, then it is de-shielding effect will be there. We'll see that. So this ability, there's the external field is able to, it will induce an electronic current in the molecule when the, and this is going to create a local magnetic field which will affect the overall force, overall magnetic force or magnetic torque. Now when you talk about dipole in a magnetic field, we are talking about the torque experience will be different, or the so net effect that you will see. So it will depending on the electronic structure near the nucleus. Near the nucleus, you can have within the same proton and the same hydrogen atom can experience, undergo, have different environment, magnetic environment, depending on how it is, the immediate neighbors are, जो इलेक्ट्रॉन है उसके आसपास कैसे distributed है, how is the electron density is distributed, what is the shielding effect. So so what we are having a current, just like in a loop, in a ring the electrons move. So see, in a similar manner you can expect something like that happening over here when the field is applied. At the center of the ring you have nucleus, so there will be effect will be there. So so it is not the actual value of shielding constant that is important for us. For most of the practical purposes, we only need to know the relative idea, which is something is more shielding and less shielding condition. So that is helps us explain most of the things. So actual values are not that important. So we are not going to focus on that. So local field, the BLOC, this is not LOC, this is local, short for local. The subscript that you are seeing stands for local, and it can be found by the external magnetic field plus the del B component. So we have put this del B is the locally produced field we are adding up, So if it is negative, if the electrons are there in a circulating in a circulated around the nucleus. So now this is the requirement. So substitute it in the, so this is the actual field experienced by um, nucleus. This is the actual field experienced by the nucleus. And so this is has to be taken into account when you are calculating the Larmor frequency. So Larmor frequency is calculated based on this, and you can, so this BLOC local field is taken into account. Gamma is the gyromagnetic ratio. So you put it, you are getting the Larmor frequency. This is Larmor frequency. Now you can see the Larmor frequency will change depending on sigma. Sigma different for same atom bonded with different elements. Same atom bonded in different ways. So different manners. So if it is a carbon hydrogen bonded to a s carbon, sp carbon, sp3 carbon, so that will matter. So you can expect and many more things are there. So immediate environment will be different, and for the same atom, so the same nucleus under different uh, conditions, different bonding situations. So that's so we come to an important point. Different nuclei, even of the same element, come into resonance at different frequencies. Same element, nucleus of the same element come into resonance at different frequency depending on the environment. It is okay. So local field will be different. So Larmor frequency for each one of them will be different. So they will be coming into resonance at different frequencies. So this is the thing, and so usually it is what you find, the way it is being NMR spectra are recorded. It is a term that is defined, that is chemical shift, which is calculated mu minus mu naught by mu naught. So what is this? It is the shift. It is the frequency at which a reference sample, a standard sample, comes into resonance, and mu is the frequency of the actual test sample, the test for which you have to. So you have a standard compared with compare the frequency of the standard with the or the reference sample with the sample which you want to know. So the standard for protons is the trimethylsilane, TMS in short. So 4 methyl groups attached to silicon. That's how you look at it. Understand this thing? So other references are also there. Uh, for 13C again, this is the TMS again, but in this TMS the carbon, the CH3 group, the carbon is 13C. The isotope is used, 13C isotope is used, because 12C is not magnetically active. So you need to have a substitute. So if you substitute this with this, then that becomes a reference for 13C. 31P phosphorus can come in, is also magnetically active, and for this the standard is S3PO4. Okay, so this scale that we are talking about, this chemical shift that we are talking about, this scale is important. हेलो, हाँ गुड आफ्टरनून. हाँ मैंने वो कल भेजा. हाँ तो कल ही दिलाना था ना, मैंने भेज दिया कल. और तेज नारायण से एक बार बात कर लो, हो जाएगा. ठीक है. ओके. हाँ, कब तक क्या पहुंचना है तुमको? पहुंच जाना है। हम लोग तो इंतजार कर रहे हैं, हम लोग तो क्लास लेने के लिए तैयार हैं यहाँ पे ऑफलाइन। कहाँ पे है अभी सेंटर नेट का? तो ठीक है, दे के आओ। हाँ तो तब क्या करोगे? नेट देना है तो फिर से अगर उड़ीसा में हो तो उड़ीसा से दे के आओ फिर। अब क्या कर सकते हैं। हम्म। हाँ ठीक है, दैट इज या यू कैन डिसाइड दैट वे। मुझे, हाँ आप लोग, लेकिन जल्दी से हम लोग तो जैसे एज पर नोटिफिकेशन यू हैव टू बी हियर नाउ। तो देखिए, हाँ, प्रोजेक्ट भी आपका मिस हो रहा है ना, क्योंकि फोर्थ सेमेस्टर फिर खत्म हो जाएगा। आप लोग अभी तो नेट का देंगे, उसके बाद प्रोजेक्ट वन का प्रेजेंटेशन देंगे, उसकी तैयारी में जब तक लगे रहेंगे तब तक प्रोजेक्ट टू आपका नहीं होगा। एवरीथिंग इज इन अ मेस, यू नो। हम थोड़ा जल्दी ये सब करना पड़ेगा हमें, क्योंकि अब अगर मौका है आपको ऑफलाइन प्रोजेक्ट करने का, यू शुड डू दैट, यूटिलाइज दैट, क्योंकि आपके दो बैच पहले के नहीं कर पाए हैं कुछ भी, बट वी आर गेटिंग अ चांस। हाँ। अ- हाँ ठीक है, कोई बात नहीं, अभी जैसा है वो करो। ओके, आई एम इन क्लास एक्चुअली, बाद में बात करते हैं। ठीक है, ओके ओके, बाय। सो क्या कह रहा था मैं? हाँ, स्टैंडर्ड्स की बात कर रहे थे कि हाँ, रेफरेंस के लिए आप कौन कौन सा लेते हैं। टीएमएस for proton, TMS for 13C, but when you are taking for 13C, you have to uh, take a TMS which is enriched with 13C. So all the CHC that you are methyl group that you are seeing having carbon of that particular isotope. हाँ, लाओ ना, क्या साइन करना है? अब चल ही रहा है, सब काम होना ही है, तो बहुत देर से वेट कर रहे हो तुम। ये सर का हम लोग का भी क्लास है। हाँ भाई, इनका खत्म करके तो तुम्हारा मैं जल्दी जल्दी तुम लोग का सेमेस्टर खत्म कराना है ना, इसमें हम भी पागल हो जा रहे हैं रोज चार चार क्लास लेके। फोटो पे भी अटैच कर दीजिए। हम्म। आज का डेट 10 तारीख है। तो तुम इतना लेट कितनी बार लाइब्रेरी का अब तक नहीं करवाए हो? सर इनरोलमेंट नंबर मिलेगा तो ना सर। अच्छा। इनरोलमेंट नंबर तो सर हम लोग ऑनलाइन में तब आया, किसी का नहीं है सर अपने। एक काम करो, ये मुहर वुहर मार लो, हम क्लास ले तो थोड़ा इसको कंक्लूड कर लें इनका। ओके, सो क्या कह रहे थे, बार बार ब्रेक हो जा रहा है। हाँ, importance of the this scale, del scale that we are talking about, chemical shift. When you describe report NMR data in terms of this, it makes sense. Why it makes sense? Because it is it is it is more convenient, because the data is now independent of the field of light. So किसी ने 10 टेस्ला पे किया हो, किसी ने 5 टेस्ला पे किया हो, आपका जो केमिकल शिफ्ट रहेगा फॉर मिथाइल प्रोटॉन और CH2 प्रोटॉन विल कम एट द सेम पॉइंट। सो उससे एक्सपेरिमेंटल कंडीशन से आपके रिजल्ट में ऑन डेल स्केल इट इज unaffected. So that is because you can see that you have the reference you are deducting, so this is will also change in the same proportion, and this del value will remain same. So 10 to the power 6. Okay, so this is our scale, or in other words, you can if you have to calculate the frequency, if uh, chemical shift is given, केमिकल शिफ्ट दिया हुआ है तो आप उससे उसकी एक्चुअल फ्रीक्वेंसी भी निकाल सकते हैं. So this kind of numericals you should be able to do. Suppose NMR is operating at 500 megahertz, and you have a nucleus which shows absorption signal at 1, chemical shift value of 1. What is the relative shift in frequency? In many books you will find that chemical shift is written in ppm, but that is many views uh, has to be found to be controversial, because ppm usually is concentration term that is used. So in some books they avoid it. Okay, so 1 ppm sometimes they write, so even if I do not write, that is same. So ठीक है, अब यूज़ करते हैं लोग, तो आप भी यूज़ कर सकते हैं, इसमें कोई दिक्कत नहीं है. यू कैन से 1 ppm, but it is not to be confused with the ppm used for concentration. Okay, so what is the relative shift? This is the question. So you can easily do this, a simple calculation. So you fit this here. This is, you see the formula आप यहाँ से ऐसे डाल रहे हो, 1 into 500, sorry, 500 hertz into this. So this is your difference, 500 hertz chemical shift into this frequency into 10 to the power 6. So this is how you get it. ये मैंने क्या लिखा? Okay, हाँ. So you have this thing mu naught, the frequency is being written del, and this is how you get this. So shift is of, in terms of hertz, the 500 hertz shift. So one chemical shift of 1 unit means uh, chemical shift of 1 means on a 500 megahertz signal, it means 500 hertz, a shift of 500 hertz. And a similar thing if you are operating the instrument at 100 megahertz, that will correspond to 100 hertz difference. So sometimes it is better, so because the separation between lines, when you analyze a organic molecule or inorganic molecule, there might be situation where they are very closely spaced lines. So if you are using a spectrometer with a higher frequency, this shift in hertz is higher and you are able to resolve it well. रिजोल्यूशन बहुत बढ़ जाता है, इसीलिए आप देखेंगे कि एनएमआर कितने हर्ट्ज का है, 100 मेगा हर्ट्ज का कि 500 का या 800 मेगा हर्ट्ज का यूज़ कर रहे हैं, उससे डेटा क्वालिटी, द quality of your NMR data is affected. So using a 500 megahertz instrument is sometimes more useful as compared to 100 megahertz, because the lines get separated in terms of frequency. You see 500 hertz difference, and here you are getting only 100 hertz difference, so the resolution is better. So we'll talk about it more tomorrow again. So थोड़ा सा timing हम adjust कर लेंगे. I have another class, so maybe we can discuss this later. So आज के लिए बस इतना ही.